quantum quantum thermodynamics. Now we are very much familiar with this branch of thermodynamics. Basically, the classical mechanics, overall classical mechanics, we can think like this: classical mechanics and the thermodynamics. These are the two basic things we use, which usually explain our macroscopic world. Macroscopic system, the macroscopic picture, we can basically get idea about using these two, classical mechanics and the thermodynamics. But in case of microscopic picture, microscopic system, microscopic world, we used to study for the microscopic world, the quantum mechanics. Okay. But actually, the thermodynamics and the quantum mechanics, though these two are very different branch, basically one is used for macroscopic system, another one is microscopic system. There is a very important link and useful connection between these two branches, and that is very much important to study a microscopic system properly. Though we are called thermodynamics, in case of classical thermodynamics or the macroscopic thermodynamics, what you can say, there is no as such dynamics actually, because in case of classical thermodynamics, we are basically deal with the equilibrium state. And equilibrium state, that means that state does not evolve with times, basically. That essentially means a static state. So though we are using the word dynamics, in case of our traditional thermodynamics, as there is no notion of dynamics basically, as we are basically using the deal with the equilibrium state. But if we look at the quantum system, the basic equation for quantum system, we know that the Schrodinger equation, or which inherently carry the notion of the dynamics. So to study that microscopic system, if we use the thermodynamics, then automatically the dynamic picture will arises, and the thermodynamics terminology will be justified. But now, first we should first start with some historical background. Then slowly we'll slowly merge these two fields, quantum mechanics and the thermodynamics, to understand the basic description of quantum thermodynamics. So now I'm starting with some historical background. We know that the quantum mechanics started with the Planck's black body radiation at 1900, and after that the photoelectric effect, that is on 1905, and also after the spontaneous emission. These experiment, these results basically establish the quantum mechanics. Though here we can see that these results, these studies are basically based on the thermodynamic picture. So, we can say that the quantum mechanics evolved with the thermodynamics in its first period. But after that, independently, quantum mechanics and the thermodynamics evolved separately, totally separately. But recently, in recent time, as we now, if we focus on our thermodynamics in basically the smaller devices, the nanoscale devices, in that case, we have to focus on the, as this system are very much microscopic system, we have to develop quantum thermodynamics. We have to incorporate the quantum mechanics in the thermodynamics picture as well. Okay, so I will start with the basic of classical thermodynamics. These are all known to us, but also I'm starting with the classical thermodynamics. Then I will introduce quantum effect on this classical picture to understand the quantum thermodynamics. So in case of classical thermodynamics, we know that the basic law, it started with the zeroth law. Okay. We know the zeroth law. Zeroth law basically describes the equilibrium state. I'm not stating the zeroth law here because it's well known to us. And I want to state the extend the equilibrium state. What does it mean? It means that we can define a state uh, with some macroscopic variable like V, T, P, volume, temperature, pressure. So using these macroscopic variable, we can define a state of that particular. Let's say if it is gas, then we can think about PV is equal to nRT. By using this equation, we can describe that state of that particular gas. So this is ideal gas equation. So essentially, this we can describe any equilibrium state with using this variable f dTp. Now here we can so now I'm here sharing this manifold. Yes, sorry. Yes. Hmm. This manifold. Okay. This is a manifold for pressure, temperature, and volume. Here, this is the pressure axis, the volume, and the temperature. We can see that each point on this manifold, we can think about any point. Each point is describing a equilibrium state because it's function of volume, temperature, and pressure. So now the transition between any two points basically means the change of the equilibrium state. Here we can think about the reversible process. In case of reversible process, uh, the transition on this green line shows the transition between two equilibrium state. Now, as we are saying that the reversible process means the process is actually, though the state is changing, we are stating the equilibrium state. Also, we are saying that the equilibrium state is changing. So this is kind of contradictory statement. Actually. So we can think like that. We are considering the quasi-static process. Quasi-static process means the process takes an infinite time to change its equilibrium state from one state to another state. And for this equilibrium process, all the states actually lies on these manifolds because, as we said, that this manifold essentially contains all equilibrium states. So this this process contains the equilibrium state. But if we look at the irreversible process, it's actually out of that manifold. This irreversible process contains those states as well, which is not described by this manifold. Now, from here, we can see the different processes as well. I'll come at that, the isobaric process, isochoric process, and the other process as well. So now this is the definition of our equilibrium state. So here, after zeroth law, we know that the first law. So in in classical thermodynamics, the first law basically is the energy conservation law. We know that is the dE is equal to d cross q plus d cross w, where d is our internal energy change, this is our heat, change in heat, and this w is our work. So these are our inexact differential. That means these are path function and this is our state function. So this heat and work, these are the most important term. We have to understand this term basically. The heat is d cross q. This heat is uh, also path function and inexact differential, but heat does not have any mechanical analog. There is no mechanical analog of heat. But in case of work, we can think a mechanical analog just like PDV. There is a mechanical analog for work. So that's why we can say that the heat is basically the useless part of the energy. We can, if we think that internal energy is classified into categorized in two parts, the heat and work, then as heat does not have any mechanical analog, this is the useless part, and the work is the mechanical part by which we can get some outcome like this. So here the d cross w is our inexact differential, though this volume or the line element, we can see this is exact differential. This pressure makes, due to this pressure, work become an inexact differential. Okay, so this is the first law, but okay, this is minus PdV. This is the convention, Now, so we can write our first law like d is equal to d cross q minus PdV. So this is totally classical picture. Now we will discuss the quantum mechanical version of this first law as well. Now, now I will discuss the second law. Just brief discussion. So we can state second law in terms of Clausius inequality. Okay. So what is that? Um, the Clausius that we know the d cross q. This is a path function and inexact differential. It does not have any, as I said before, mechanical analog. But Clausius first introduced that we can define d cross q by t as a state function, and that is entropy. Okay. So and this is entropy is the state function, and thus we define that if we calculate that these relations should always hold. So this is actually the mathematical version of second law. That for the reversible processes the equality holds, and for the irreversible processes there should be less than zero. So what does it mean? It means that the entropy change for irreversible process is always greater than that the reverse if it is through a reversible path. Or we can say that, as we know, that del S universe is always greater than zero. This is the second law. So from Clausius inequality, we can say that our second law is just that always for any processes the overall entropy of the universe will always increase. Okay. So now I'm not getting the third law because third law is a little bit different from the Nernst theorem. We know that. I'm just writing the third law, but I will not relate third law with the quantum thermodynamics. The third law is just limit if temperature tends to zero, then del S will be equals to zero. Okay. So these are basic laws of thermodynamics: zeroth law, first law, second law, and third law as well. But now, if we look at the classical thermodynamic processes,
Shuvodip.
yes.
So third law, limit t tends to zero, del is equal to zero, absolute entropy equal to zero.
No, del S should be zero.
Absolute
For any process,
entropy.
no, absolute entropy, not absolute entropy. If entropy change for any processes when the temperature is tends to zero, then del S will be zero for any chemical or physical processes.
Okay.
Absolute entropy will be zero for any perfect crystal.
Yeah.
But for anything, if temperature is tends to zero, then del S will be always zero for any material.
Yes. Yeah, that's.
So it's basically the Nernst theorem. Okay. So here we will discuss our classical thermodynamic cycle. There are three type of cycle I will discuss. First is we know very famous Carnot cycle, then Otto cycle, and the Stirling cycle. These three cycles we will study. Then I will introduce the quantum mechanics. Okay, to study this cycle, I will recall the processes. That means the isothermal process. We know for isothermal process, the temperature is fixed. Next is our isobaric process. We know these things. Isochloric and adiabatic basically. Here the D cross Q equals to 0. There will be no heat exchange. Okay. Now, for any, now I'll start with the thermodynamic cycle, the Carnot cycle. Okay. So, we have to, because we know that any equilibrium state can be defined like N, V, T or P, pressure, temperature or volume. Here we are choosing that pressure and volume. Okay. So for any cycle, because this is a cycle and these are the all state function, so obviously over a cycle daily the internal energy change should be 0 and the entropy change should be 0, because these two are also state function. So let me start with A. Okay. So this is our Carnot cycle. The first is our isothermal, where T is 0, temperature is constant. Then this is adiabatic, again isothermal. I will not discuss full derivation of the efficiency. We know that very well. I will just relate this cycle with quantum thermodynamics later. That's why I need to discuss the efficiency. We know the efficiency is defined like the work done on the system and the heat absorbed. And for Carnot cycle, the efficiency is 1 minus TH by TC. TH is the higher temperature and TC is the lower temperature. This is divided by TH and this is TC. Okay, this is Carnot cycle. But now the Otto cycle.
So what is the
For
physical example of Carnot cycle? Like any real life example?
yes, any engine we can think about, the mechanical engine runs to Carnot cycle.
Okay.
And also we have to remember that the efficiency of Carnot cycle is the is highest. For any reversible cycle, we can consider other cycle as well, Otto, Stirling, but the efficiency of the Carnot cycle will be maximum. For any possible reversible cycle, that is the upper bound of the, and we can verify any result with this limit, the Carnot limit. If it is beyond the Carnot limit, then we can think about there is some flaws in that experiment or that result. So we thought, not thought, we considered that the Carnot limit is the upper bound for any thermodynamic cycle.
Okay.
For Otto cycle, the cycle is like, to draw this. Okay. This is also for P and V. Okay. We start with adiabatic process, A to B. Then it is isochoric. Again, it adiabatic compression, and again isochoric. For this Otto cycle, I think it's understandable. This is isochoric. This is adiabatic. Isochoric. For the Otto cycle, the efficiency is down. This is the efficiency for the Otto cycle. And last one is the Stirling cycle. And this is the most important one, because for in case of quantum system, the Stirling cycle is more realistic to experimentally verified, and the Stirling cycle is actually experimentally verified for quantum mechanical processes, or Stirling engine we can say. Let's say Stirling cycle. The Stirling cycle is the same like the Otto cycle, just adiabatic strokes are replaced by the isothermal strokes. This is isothermal, isochoric, this is the Stirling cycle. Okay, so now we have
Like
to
any
carry out
example?
for Stirling cycle.
Stirling and Otto?
No, we can prepare any engine, any engine using this that may be
Yeah.
carried out through Carnot
Yeah,
cycle
that's
or
what
Otto cycle.
Yeah, any real life machines we can think about.
Um, No, that I don't know. I think basically we used to follow the Carnot cycle, but still auto cycle or the Starling cycle also can be used for making any engine, because these all are reversible cycles. But and these are actually the as these are reversible cycle, we can't experimentally made the engine following the cycle properly. We have to introduce that finite time thermodynamics. If,
Mhm.
if time permits, then I will discuss that later. Because we can't make the reversible processes. We have to consider the
Yeah.
irreversible processes, which
Mm.
because in what happens in as these are the reversible process. That means as I mentioned before, these are the quasi-static process. Means for changing one state to another state from let's say A to B, it takes
Mm.
infinite time. That means for experimental use, that efficiency uh, is not everything. We have to look at the power. But in case of power, there is time. For the
Mm.
reversible cycles, the time is infinite. So essentially, the power will be zero always for any reversible cycle. So that's why, and also then in reality, the reversible processes are not possible. We have to consider the irreversible process, which make the time finite, and that is the finite time cycle, which deviates from these reversible cycles little bit. So using that cycle, so we can actually that cycles are usually followed to make some engines. For that, we use the Carjon-Albon efficiency. I will discuss that later. Time is.
Okay, got it.
Now, this now I will introduce the quantum mechanics because these Carnot cycles, these reversible processes, these laws, everything is valid for classical system or macroscopic system. That means there are infinite number of molecules. Everything is there. But if we look at the microscopic system, then there is there is no infinite number of molecules. We have to focus on each and every molecule. So as the molecules follows the quantum mechanics, we have to relate the quantum mechanics and thermodynamics. And to relate quantum mechanics and thermodynamics, the in between the main important thing is the statistical mechanics. You then only we can relate quantum and thermodynamics, these two different branch. And statistical mechanics is actually relates the quantum mechanics and the thermodynamics, because we can think about that. Let's say for any quantum mechanical particle, we know that for any quantum mechanical particle, if we calculate the average value, because we know that quantum mechanics is totally probabilistic. If we want to calculate any physical observable, we have to take the average. So this is the average. This is quantum mechanical average, which is defined like this. Okay. But now if we study the thermodynamics, then we have to focus on the the statistics of that particle as well, because there are lots of quantum mechanical particles. So for actually we need to study the quantum statistical average, not only the quantum average. This is the main element to study the quantum thermodynamics, this quantum statistical average of any physical observable. So we can define this like this: quantum average and then statistical average. So for any statistical average, we can write like the probability and the quantum average. And if we expand that, then we'll obtain. Okay, this is our quantum statistical average for any observable, where p psi is the probability of finding of state psi. So now we can write like this: p of psi trace over a psi psi, because we know that uv can be written as v of u, trace over v of u. Okay, this is the inner product, and this defines as just a number, but this is some operator. This is operator. If we trace out that, then that will be equal. Okay. So now, uh, It can be written like this, p side, again, and yeah, okay,
Shubhadeep,
yes,
before you move ahead, in the classical part, I got stuck in somewhere. Like, could not process when you said about that cycle that
mm,
it takes infinite amount of time to move from A to B. Okay.
mm,
Yeah. So experimentally, you will always get power equals to zero. So if
yes.
A to B only takes infinite amount of time, then how? मतलब then cycle ही क्यों होगा?
No, these are the as we can think the ideal gas. Ideal gas does not exist. Not like this. These cycles are reversible cycles. These are the ideal cycle. We for
Okay.
ideal cycles we are considering the reversible process because our total thermodynamics we study the equilibrium thermodynamics as we said before. There is no each states are equilibrium state from let's say not A to B from A to some B state. This is also from here we can see from here to here this process is if it goes through the reversible path that means each and every point is equilibrium point on this path. So equilibrium point means that will not evolve with time. That is the definition of equilibrium state. There is no change with the time. So that's why I said that it should say that it should be thermostatics like that. But though we are talking about some process, for process the equilibrium state should be changed, and this is like the contradictory statement. Equilibrium state means that should be that should not change with time. Also, we are saying that that is changing with time. So that's why we said like this. This is quasi-static process means the process the state changes but it takes infinite number of time which means that the state is quite steady in equilibrium state. So
But
in that way if
equilibrium is also but equilibrium is also of two types, right? There is a static equilibrium, there is also a dynamic equilibrium where things are changing. But macroscopically it's not visible.
macroscopically it's totally in case of equilibrium state is static equilibrium, not dynamic equilibrium means that is in case of dynamic equilibrium there that means that in both way the rate will be same, then it is the dynamic equilibrium. Dynamic equilibrium is different thing. This is the static equilibrium totally. Equilibrium means the basically it means that there is no evolution with the time.
So you're saying whenever in thermodynamics we're talking about equilibrium, it's always static, it's not dynamic.
It's always static. That's why the thermodynamic terminology is not correct actually. Though it is
Okay.
dynamic, but here in his previous time it was used dynamics because they are talking about the heat flow and because the thermodynamics evolved to describe the heat flow, heat and work.
Mm.
And what happens that heat is they consider heat as fluid not as the energy. Later on it was finding out that heat is form of energy but they consider it as fluid. So that's why they introduced the term dynamic because they thought that heat is flowing. That means one kind of fluid is flowing. So that's thermodynamics we have studied before. That is totally not dynamic. That is static. So that's why to introduce the change in the state, the equilibrium state, we need to consider the quasi-static approximation because it's actually static, but we are considering that takes infinite time, so it's quasi-static. So
Okay.
not the cycle, any process should not be completed in a finite time for any classical thermodynamical process. Is it clear?
Yeah, it's fine. You can.
Okay, so we can write this like trace over a rho. This is our density operator. So density operator rho is defined like p psi over psi. Okay. Uh, for pure state there will be only one state. So for pure state, the rho is just this, and this is the general description for pure and mixed state as well. Okay, so now this is quantum statistical average. We can write like this, trace over arrow for any uh, observable. That can be energy, that can be any other physical observable like entropy uh, state function. So now first we have to define the now equilibrium for quantum sense. We discuss the equilibrium state for macroscopic system, the classical system, but we need to define the equilibrium state for quantum mechanics. So for quantum mechanics, we know that the Hamiltonian, this H Hamiltonian, we have parameterized the Hamiltonian with some lambda. I'm not capping using the cap. This lambda may be anything. For let's say for harmonic oscillator, we can think like the omega is lambda. Lambda is just a parameter which controls our Hamiltonian. So we have it may be some electric field or external magnetic field as well. Okay. So now we are saying that any quantum system for let's say this is some quantum system. In case of classical thermodynamics, we are considering system and surrounding. Here also we will consider some quantum system, and the rest of the part is the surrounding. Just system is quantum. Otherwise, it's the surrounding is not quantum. It's not quantum. That is in general our surrounding, the classical surrounding. The system is quantized. So we can. This is important because in case of quantum system, in case of quantum system, we know that in quantum mechanics there is no as such concept of temperature. There is no temperature. Okay, but as surrounding is classical system, so there is in surrounding there is temperature. So this part is important because I forgot to say this. The thermodynamic limit. I'm saying thermodynamic limit is that classical thermodynamics is valid when n tends to infinite, v tends to infinite, but nv that is finite. That should hold. But in case of quantum mechanics, what happens? This n and v, this thermodynamic limit is not valid. So how we can define a state, equilibrium state in case of quantum system? So that's why we need some definition, and that is the Gibbs state, the density of in case of the equilibrium density operators.
Shuvodip.
That yes.
Yeah, so this thermodynamic limit I did not get. If n is to infinity and v tends to infinity, then n by v, how come it's finite? Because infinity by infinity cannot be finite. No?
Yes, if both tends to infinity, then the ratio will be finite. Let's say if n goes to 10 to the power 23 and volume in the order of 10 to the power 22 or something, then n by v is not going to that order. So it will be just 10 or 100.
Okay.
Just we can think about our classical macroscopic system. There, the volume is the number of particle is finite, and the volume is also we can think about for that particle. Respect to that particle, the volume is also finite, but that n by v ratio that should be in the finite range. Otherwise, these all classical thermodynamics laws, everything we studied under this limit. Otherwise, that laws will not be valid. We have, that's why in case of quantum mechanics, as this limit does not hold, we need to introduce new definition of the equilibrium state and the other laws.
Also, mathematically, L'Hospital's rule, you can think that to check whether some ratio is finite or infinite, you can apply that rule.
Okay, that I don't know actually.
In the infinite, at the limit tends to some infinity or some zero. So you can check the ratio. Means if you put the value, direct value, it will be infinity by infinity or 0 by 0.
Yes.
So but that is not the correct way. Then you have to check the gradient, okay, and then see there is convergence. They converge to some value or not. So Air Hospital rule in 12.
Okay, Yale Hospital.
Yale
Okay,
Hospital.
okay, yes. Okay, yes.
Mhm.
Now I remember.
Okay.
Okay. So now we are considering that quantum system. This quantum system is weakly, or we can say the ultra weakly coupled with the surroundings. Okay, the coupling is very weak, and under this ultra weak coupling, we can describe the equilibrium density operator of that system. We are dealing with the system always by the Gibbs state, which is defined like this. This is the density operator. E to the power minus beta h. H is the Hamiltonian of the quantum mechanical quantum state, and z. Z is the canonical partition function. We are considering the canonical ensemble. That means only the energy can be exchanged. So z is defined with trace over e to the power minus beta h. Here the beta is 1 by kBT, inverse temperature. So this is important. This temperature is not, this is the temperature of the surroundings, not the quantum system. Because as such, as I discussed before, for quantum system, there is no definition of temperature. But as we considering equilibrium state, this quantum system is with equilibrium with the surrounding. So we can think like that, the temperature of the quantum system should be equal to the temperature of the surrounding. And surrounding is a macroscopic system. We can think like that. This is that follow the classical thermodynamics. So there should be a notion of temperature. So this temperature is the temperature of the surrounding. If we now if we think if the surrounding is also quantum mechanics, yes.
So here rho equilibrium is the density operator of the whole system, right?
No. For the system, not
For the
with the
quantum
surround.
system.
For the quantum system, because the Hamiltonian is this Hamiltonian is the system
Yeah, so
Hamiltonian.
yeah.
That is
But
that I'm
then,
saying. This is
yes, but then why we are dividing with Z?
no. Z is the partition function. So for density operator, so this
Like
is
you
some.
are writing Z equal to trace over exponential minus beta h, right? So here h is the Hamiltonian of the quantum system or Hamiltonian of the total system?
No, this Hamiltonian is the for quantum system, not
So,
including the surrounding.
Yeah, that makes sense. Yeah.
This Hamiltonian,
So
both Hamiltonian are the same.
only temperature comes from the surrounding.
Yes, only temperature and because it is canonical ensemble. Let's say if it is grand canonical, then the chemical potential will also come from the surrounding, and that is because the system is with equilibrium. Otherwise, that temperature we can't define. So that's why we have to define the equilibrium condition. Otherwise, in case of quantum system, we can't define the temperature.
Yes.
So now this is the rho equilibrium. Now easily we can now for this quantum system we have to define the energy, the internal energy that should be this, as I mentioned before. So we can write this like this way or the same thing, because in trace we can exchange. Okay, so if we take derivative dE, then we can write this trace over. I'm not keeping that. Okay, so this thing we can write. Now if we relate with our classical thermodynamics, that is d cross q plus d cross omega. Here these two terms are essentially the same thing. This is our d cross q and this is our d cross omega. So from here we can relate the heat and work in case of quantum thermodynamics, quantum mechanical system. So for quantum system, the heat is defined like trace over rho equilibrium H. Here the rho equilibrium is changing. That means the population of each level is changing. and in case of the work, rho equilibrium is fixed, the Hamiltonian of the system is changing. This is the definition of our heat and work for quantum mechanical system.
This is unsuch or means
This
is some type of unsuch, means there is two, means this does not mean that dq equal to this or dw equal to this, means.
Okay, no, we can think that if we provide heat to any system, then population will change essentially. So that means the heat should be related with the change of population. That's why this term is related with the heat, and the rest term should be then the work.
Okay.
That way it is related because heat it is defined like this. If the temperature increase for in a system, it may be quantum system also, then the population actually gets changed. No? That's why the rho will be changed, the d cross q. In that way, we can define the heat and work. In statistical mechanics, also in canonical ensemble, we also define like in that way the heat and the work.
Also, it also means and to connect with other properties of heat also, means dq is inexact differential. Okay.
The inexact difference.
But here this term also inexact, means it is dq is not state property.
No, dq.
But here d rho equilibrium h, it is for a particular state. I think we can get a value for that.
Yes, we can get a value. But
other property I want to check, means whether this mathematical property of dq also holds for this right hand side trace of d rho h.
Okay. That means it will be inexact or the exact difference.
Yeah. Means your logic is okay. That it what the heat will do means heat exchange will exchange the population. Logic is okay, but in mathematical terms, is it? That's why. Is there any derivation other or?
Yes, like
no.
Is it equal to d cross q or it is proportional to d cross q?
No, it is considered the equal to d cross q.
Okay.
But just looking on this form, it's difficult to predict whether it will be exact or inexact differential.
Okay.
But okay, I have to think on this. I'm not thinking like this. Okay. But it should be
exact. Generally,
yes,
state function is connected to the exact. Yes. So.
Okay, but for timing.
Yeah, we will think. Yeah.
Okay. So now this is the another important properties are entropy, and for quantum mechanical system, the entropy is defined with the von Neumann entropy. And von Neumann entropy is trace over rho L entropy. This is our von Neumann entropy. So if we differentiate again, then we obtain. I'm not doing these steps. These are mathematical steps. For equilibrium state, rho will be replaced by the rho equilibrium. F, where F is our free energy. Equals to the LNZ. So this is our ds. So now, if we consider the isothermal process, let's say for isothermal process, this can be derived easily. If we put the value of F df, then we can derive this. For isothermal process, in classical mechanics, if we look at the classical mechanics, that d is equal to d cross q plus d cross w, and if it is the isothermal process, then and also the dg is equal to vdp minus sdt. So for isothermal process, this is 0. the temperature change is 0. So we know that for isothermal process, the D cross Q is equals to the dg. Okay. For here also, if we consider the isothermal process, similarly, analogously, we can say that for isothermal process, dF should be also equals to the work done, D cross W. Just like just with analogy with our classical thermodynamics, we can say that. Now, if it so, then here for ds, this is our d cross W. This part, this is our d cross W. So this will be cancelled out. D cross W and df will cancel out. And for isothermal process, the ds will be just beta trace over this h. And you can write like this. This is our d cross q by t. So here, or we can like this is beta d cross q is better. So it's consistent that ds is equal to beta d cross q, and this is again we know that this is d cross q. That's why from here also we can say now if we consider this, then everything is consistent. We can write that ds is equal to beta d cross q.
Oh, just 1 minute, wait 1 minute. Means I just back of the mind I used that expression to derive that expression earlier.
No,
So I have
that
to
is not
think
used.
in okay. I was thinking in wrong way. So here for H to DS, when
Here I
you
start with different definition. I'm not using that.
yeah. That's why I was wrong. Means I back of the mind I just consider ds equal to dq by t. So then I derive that equation. But how I can get this h to ds here?
Just derivative, just taking derivative and using the
taking
formula of
derivative and okay using the formula of okay, and
f. Yeah.
z for z.
Z is the canonical ensemble partition function. This trace over e to the power minus beta h.
Okay.
So
If we take the derivative of
that,
this part, okay.
if we put that, then that equation can be derived.
Okay.
So,
Okay.
so just using that isothermal, considering isothermal process, we can establish that this part should be the work and this is the heat. Then everything will be consistent with the previous result.
Then
So we can write d is equal to kbt ds plus tf for in general case. No, not in general, for isothermal process. Okay. So this is from here we can define, now it is clear how we can define the heat and work for isothermal for quantum system. But now we did not use any form of Hamiltonian. That to have that the form of Hamiltonian is important. Otherwise we can write this. So in general, as Hamiltonian is parameterized with lambda, we can write the Hamiltonian is just En and the n. And also n will be just lambda like this.
the above
So,
expression, how does it different from this classical equation? Means just to I want to
this one.
understand better. Yeah. In the classical
No, this is
if I write
same
T
equation
equal
for
to
classical.
same. Okay, TDS du equal to dq
Just
plus dw. Okay.
hmm.
So dq equal to TDS and
Just kb has here.
kb. There is another kb is extra. That's what I want to understand.
Kb is extra. Otherwise, it will be just TDS plus
Okay. kb is extra for
extra
this quantum.
quantum. Yes.
Okay.
So this is our, in general, we can write Hamiltonian for any quantum mechanical system like this, the sum over the energy state and the eigenvalue. So now, if we put that, so we can write the energy of US, it should be sum over n, Pn, En. The Pn is the probability of finding state, n state, and En the energy. This is parameterized with lambda. So here, using that,
so dimensionally it is consistent like previous equation.
this one.
No, the energy equation, D, yeah. So KBT is thermal energy, E is
KBT
thermal
is energy.
energy,
Yes,
but
yes.
S has different unit, right?
Okay.
S is Joule, mole inverse, Kelvin inverse.
No, I think these are the quantum mechanical dimensions. Okay, 1 minute, 1 minute.
The quantum or classical, it should be
The
dimensional.
dimensionally should be consistent. 1 minute. But beta should be there. Beta is there. So
Yeah,
beta
beta
will
should be
come.
there, but
Okay, in the expression of S, I think, go to the
yes,
earlier
yes.
equation,
It
is there is a
in the
beta.
expression of S, it is already consumed.
Yes, S is dimension means. Yeah.
In S there is also beta.
Okay.
So,
In your
Yeah,
S, there will be KB. I think this KB will be absorbed into DS. Then it will be consistent. Means, am I thinking correct?
yes, because if we put that, then I think the KB and the beta and KB will cancel each other. Then it will. I think,
It will be the same analog to the
D cross Q will be there.
Yeah.
I think that here this entropy I think is not the same dimension with the classical one, because in case of classical case that will be just 1 by T D cross Q. So dimension of entropy is different from the classical entropy.
Now, if we put beta there in the entropy equation, go to the
Here.
just entropy equation here. If we put beta here, means then it will become consistent.
Actually, I think here the KB we can put. If KB is there, then
yeah, KB. If we put KB here, sorry,
yes,
not
then it will.
KB here.
Then that will be consistent.
Then it will be consistent with the classical analog. Yes, because in classical
then,
entropy definition there was KB. This is the
there is KB.
There is KB.
That's good. Here, as KB is missing, the factor KB appears there.
If it is adsorbed, then within DS, then it will be the same.
Yes, right. Okay. So now this is our energy. So now just taking the derivative, we can write this. So it is always parameterized with lambda. I'm not writing again and again. So again, we can relate with the work and the heat. So now I am taking a realistic case that this is in general. Now we can define, we can explain our system considering basically the simple harmonic oscillator. So in that case, the Hamiltonian will be h cross omega and there should be half, but we are not considering the half because that is just a constant term. So if we consider that h cross omega n bar, then for E will be average of H. So it will be h cross omega n bar. This is our, as we are considering the harmonic oscillator, this is our Ghosh-Einstein distribution function, or the Ghosh distribution function, we can say, which is 1 over e to the power beta h cross omega minus 1. So if we consider the fermionic system, then it will be just Fermi function instead of the Bose function. So here we are considering harmonic oscillator, so the energy will be h cross omega n bar. So dE should be, this is the general form for any quantum system. We can write this, but for harmonic oscillator we can write like this is. So again, we can here relate the d cross q and the d cross omega. So here the work done, this is our h cross n bar d omega, and the heat is with the same analogy, because if we provide the heat, then the population, this n will be changed. So that's why this is related with heat, and this is related with the work done.
What is capital N operator? What do you mean by that?
Number operator.
Okay.
That means the A dagger A. So we can write the Hamiltonian of simple harmonic oscillator like this is so this should be half here, but you can ignore that. So this is our Hamiltonian of simple harmonic oscillator. If we we can write like this. If we operate this Hamiltonian, let's say H on any state, n state, then the energy. If we consider this, then it is there. It's well known that A dagger is the number operator. You can take the form of number operator A dagger, and then you can operate the Hamiltonian on the any state, and you will get the same result for we obtain for harmonic oscillator there. So, okay, is there any confusion?
Yeah.
Okay. So this is our work and heat. Now, using this is the definition of work and heat. Now, last I will just using this definition of work and heat. I will introduce the cycle, thermodynamic cycle, analogously with the classical cycle, as we discussed before the classical cycles. So here, instead of PV, in case of classical cycle, we use the PV. Here we will use the n omega. Okay, because we can see here for classical case, because Q is just PdV. So P is here some n bar is there, and again for in d cross Q, in d cross Q the volume changes, so that V appears here, and here the omega is there. I will discuss. Just one thing here, this omega is related with the volume actually. The omega is related, not proportional, is related with the inverse of the volume. This is the main important thing. Otherwise, we can't explain. We have to, from these two relations, we have to consider that the omega is related with the inverse of volume. Then we can explain the thermodynamic cycles, quantum thermodynamic cycles. So first, I will discuss the quantum Carnot cycle. So the strokes are same, just the variables are different here. Variables are n bar and the omega. It will start with the isothermal process, but from here it will start like this. Okay, then this is the adiabatic process, and again this is isothermal, this is adiabatic. Okay, now for isothermal process, isothermal process we have previously discussed the forms. This is the isothermal process. Here A to B is the isothermal process, but in case of adiabatic process, in isothermal process both n and omega is varying because nothing d cross q and d cross q and d cross w both are non-zero, so both will be changed during the isothermal process. You can see from here. But in case of adiabatic process, what happens? The d cross q is 0. So as d cross q is 0, from the form of d cross q, this is the form of d cross q. If d cross q is 0, then dn should be 0. This is state function. Dn should be 0. If dn is 0, then n should be constant. So here
How did you relate this n bar to pressure? Like
n bar to pressure.
Since in the
No, I did not relate with in case of in case of classical picture, we plot the v p and v na. So here the variables are the n bar, not n bar and the omega. N bar is the population, average population, and omega is the frequency. So we have to plot with these two variables. There are
yeah, but you related the omega to volume, right?
yes, I related omega. Omega is related with the inverse of volume. So
And
that
you
we have.
also said there is nothing called temperature in this. So how can you define isothermal process?
No, the system is equilibrated with the surrounding.
Okay.
So in that way there is temperature. If there is that is not equilibrium, that's why I am taking a rho equilibrium everywhere. All there is rho equilibrium. In that row equilibrium there is beta, and in beta there is temperature. That temperature is the temperature of surrounding.
Are omega inversely proportional to V, that is related to the density of states, right? If you decrease volume, then the space between two energy level will increase. So in that sense, the frequency of the harmonic oscillator will increase.
Increase.
Okay.
So, so adiabatic process is clear. So now again it is isothermal and adiabatic. So in quantum scale, in n bar omega, the Carnot cycle is defined like this. So similarly, we can define the Stirling cycle and the Otto cycle. So first, the Stirling cycle.
Could you say any dependency between n and omega for isothermal? Means any analytical dependency, that like isothermal, classical isothermal process, those are P proportional to 1 by V. Okay. So for ideal case. Similarly, is there any functional dependency here? Means for
No, we can think like this, because here let's say this is isothermal. Here the omega is decreasing from A to B. So omega is decreasing means we can say the volume is increasing. So it's the expansion, isothermal expansion. In that way we can think.
okay, but any means
No,
explicit.
in quantitative, no, it's just qualitatively this is.
Okay, just qualitative. Okay.
Okay. Okay. So for Stirling cycle, we know that for Stirling cycle, strokes are isothermal and isochoric. So this is the isochoric stroke, A to B. Okay, isochoric means the volume should be conserved, dV should be 0. That means the d omega should be 0. So if d omega, that's why it's parallel with the n bar. The omega should not change with the isochoric process, as we related the volume with the omega. So again, then this is isothermal to C. Then it's again isochoric. Okay. Okay. This is isochoric, isothermal. So this is our quantum Stirling cycle. And okay, draw. One minute. I did this, but I have. And the last one is the quantum Otto cycle. Okay. Okay. So for quantum Otto cycle, I have to just replace the isothermal stroke with the adiabatic stroke. So this quantum Otto cycle is very important, interesting actually, because this is at a time one either omega or n bar is constant. If it is started from here, A, B, C, D. This is isochoric process, so omega should constant. This is adiabatic process, so n bar is constant. So interestingly, for Otto cycle, the quantum Otto cycle is most interesting among these Stirling, Carnot, and the Otto. So these are the quantum thermodynamic cycle. So the efficiency we can write for the cycles for quantum Carnot cycle, the efficiency will be the similar with the normal thermodynamic cycle. And for the Otto cycle, for Stirling cycle, it is difficult to find out the efficiency, but for Otto cycle and for Carnot cycle, we can write. For Otto cycle, the efficiency is omega c minus omega e. These definitions are there. These definitions are not very much difficult. We can derive this.
One thing that the nomenclature isothermal is okay. Temperature is constant. Okay, but nomenclature of adiabatic is also okay, but isochoric means volume does not change,
Volume does not change.
but the volume does not change. That does not mean that there is no other energy, there is no other work. Okay. So the mechanical work is 0. But means there are possibility of other works. Means mechanical is only one subset of work. Okay.
So here omega
Yes.
is frequency.
Omega is
What-
frequency.
Omega is frequency, means isochoric. That does not always mean that d omega equal to 0. Means isochoric, that does not always mean that dw equal to 0. Means work equal to 0. Work done equal to 0. Is it?
No, in classical case, isochoric always means that volume is 0. So that is also
Volume
the
is 0.
mechanical work.
Mechanical work is 0, but means there might be other source of work.
There might be other source of work. Here also,
Then-
we are not.
Okay, you are considering only mechanical.
No, here if the volume change is 0, if dV is 0, that does not mean only the mechanical work. But if dV is 0, then d omega will always 0, na?
Now dV is 0, then dw mechanical work is 0.
Mechanical. I'm not saying the work is 0. I'm not saying that.
Okay.
The d omega is 0.
Yeah, but so the d omega is the frequency difference. Yeah.
Okay. Frequency
That will be
difference.
0.
Yeah, omega is related to 1 upon v.
Omega is related to
1 upon v.
Inversely dependent on the volume.
This is the volume is the omega is the system frequency
For harmonic oscillator.
Harmonic
Yeah.
oscillator, and this volume is the overall volume, means system plus surroundings volume.
Yes, we can think the volume is for the classical case. If we make analogy with the classical case, then in classical case there is a volume. In quantum case there is no notion of volume.
Yeah, means here with there you connect volume means what I understood that it is system plus surroundings whole volume, just like
Whole volume.
temperature.
Yes, if we decrease the volume, then the frequency of harmonic oscillator will increase in that way.
But that is, if I understand, based on only systems volume. Means there is my harmonic oscillator is much more confined. Okay. Then the frequency gap will increase. That is okay. But here this volume is not that volume, na? What I
No, in classical case volume is different, but when I relate with omega with the volume, then that volume is the volume of the system volume. Then only we can relate with omega and volume.
oh.
But in case of classical work done, that is different. That is different. But
Yeah,
if we think of we know the classical isochoric process. In classical isochoric process, volume change is 0. Now, if we say, let's say the quantum isochoric process, in quantum isochoric process, the volume change would be 0. But
volume
this
change,
is
yeah, that's logic is okay. Then I come back to the quantum isochoric process. Means then how do we change how do we control the system volume? Means volume change is 0. That is okay in the system's perspective. Then how do we control?
But this volume for quantum case, this is not same with the volume change in the classical one. So in case of that is difficult for quantum case, no? The concept of volume. That's why we have related volume with the frequency. So if volume change is 0, then we can say that the frequency change should be also 0. Then d omega should be 0. So d omega 0 is defining the quantum isochoric process.
Yeah, means that is okay. Means now I understand that part, that you connected the volume means with respect to the system, means this quantum
Then
system.
only we can relate the omega and the v.
Yes. Then isochoric means if we define for a system, practical system, it is isochoric at quantum level. That description would be difficult, no? Means
yes, for quantum level, the description for isochoric process is most difficult. Adiabatic and isothermal is relatively.
Yeah. That is easy. Yeah, means just like Otto cycle looks simple, but
looks simple, but
that isochoric part is means we have no idea how to define
but
say.
but mathematically it's easier, because mathematically we have to put the omega is 0.
Mathematically it is easier. Yeah. But that means at the end we have to describe some engine based on
Quantum process.
based on this. Yes. There
That's why
we have
always
some prescription. We need some prescription how to define the volume there, means how to define isochoric there, isochoric process.
we don't need to define volume, because we can define the isochoric just using the frequency, the volume. We can
Okay.
So here main thing is like this frequency. So here connection with the volume is just to
Just nomenclature, just for nomenclature.
Just nomenclature.
Okay.
So
That's what.
Only thing, only thing is the frequency change. The frequency change is 0. It means it's isochoric.
Yes. Now I get it.
Yes.
Okay.
So these are the all quantum processes. Just at last, I'll not discuss the total the finite time thermodynamics, because there is no time. I'll just mention that the limit, the cardinal one, in case for this is not quantum, this is classical, but this is important. That we know that for as I mentioned before, for our classical thermodynamics, that takes infinite time. So for the in case there is no power, as power should be 0 for classical thermodynamics always. But if we consider the irreversible processes, then or the finite time thermodynamics, then we can define the power basically. I'll just draw that curve, and this is our Carnot cycle normal. So okay, so this is adiabatic, this is isothermal, adiabatic. So now if we consider that the system, the classical system, this is connected with the surroundings. So what happens in case of our normal thermodynamics, traditional thermodynamics, there is no time, but here we have, for introduced time, we have defined that the temperature of surrounding is different with the temperature of the system. Then only we can introduce a time. Let's say it is H. Okay, I'm drawing properly. Let's say we know that the Carnot engine, right? Like here is a system, heat in hot bath to cold bath, the heat is flowing. This is connected with reservoir, this is connected with reservoir, like this. This is our system temperature, hot bath, and this is our for reservoir, THR, this is TCR, this is C. Like this, then we can define the finite time. Otherwise, if this the equilibrium, we consider this is equilibrium temperature. This system is always with the equilibrium temperature, equilibrium with the surrounding. Then only the H will be equal to HR. And in that case, our classical, the traditional Carnot cycle will be generated, and there will be no sense of power. So if we consider this picture, including HR is greater than H, greater than C, greater than CR. Then what happens? The heat will be flowing from here to here, then here, then here, like this. And this heat flow is can be written like this. UH is H time. This is the time. HR minus TH. Just this is the Fourier's law. And for this part, this will be KC, kappa C, tau C. So if we put that, this QH and QC, and then we can also calculate the efficiency and the power. The power will be just defined like this: QH minus QC divided by one constant. Okay, we can ignore that constant. Just TH plus TC, like this. Because this is the time, total time, TH and TC. Otherwise, in other processes, there is no time. The time is involved in there. So we can write like this. This is the power. So if we calculate that, the power, then we obtain that the efficiency at maximum power. This is the efficiency at maximum power. I'm not deriving, the derivation is very beautiful. Power, that will be 1 minus over TCR by THR. Just it is replaced by square root. In classical, in traditional thermodynamics, the efficiency is just 1 minus TH by, but here just is replaced by square root. This is the cardinal bond. Cm is the cardinal bond efficiency, and the actually in all the in our experimental case or the industrial case, this is considered as the limit. For the efficiency, this is considered the cardinal bond efficiency. This is considered. So for that, we need the finite time thermodynamics, the derivation of finite time thermodynamics. But I'm not derived here, but this is very important actually. So this is the classical case, but I just discussed the cardinal bond bound. Okay. So with this, I think I'm done. If there any question, you can ask.
And here in the classical analog, go to the last slide. The classical analog, their reservoir and system temperature is same, no? TH. Those are in equilibrium.
In traditional case, we consider that the TH is equals to THR. That means system is equilibrium with the reservoir.
Yes.
But then there will be no notion of time. That will be equilibrium case. To introduce time, we have to consider that this reservoir is temperature is THR and the system is TH. Then heat will flow from system to reservoir to system as HR is greater than H. And for that, gamma H time, the tau H time is required.
Tau H is, what is tau H?
This is the time.
Okay, time. Okay, time.
That's why here come tau H plus tau C. Because other processes are in that case, if you consider the cycle, in this cycle, there in other processes there is no time. Time is only there from here to here and from TC to TCR. So overall time to complete the cycle is tau H plus tau C.
Okay. And
so if we okay,
this is classical, means
this is classical.
Is classical. You derived here.
Yes. This is classical, and this is used for studying any engine. For any engine, we actually don't use the Carnot limit because that is totally ideal case in the reversible Carnot cycle. For check the efficiency or the efficiency at maximum power, you always use the cardinal bound for industrial case as well.
Okay.
That's but if we discuss the total derivation, then it will be more clear. But
okay.
So, Shuvodip, so how would you actually design a quantum engine, like knowing the, let's say, auto cycle of a harmonic oscillator immersed in a bath? So how would you design that?
Okay.
Like in practical sense, so we are main purpose of quantum thermodynamics is to like use this logic to build nano engine, nano machine, right? Of higher efficiency. So how would you design that?
Okay. I have think how to design practical case.
Like from the experimentalist perspective, like how experimentally actually think about it.
Okay.
I don't know. I have no idea.
I have also not okay, I have to also think, but I think
people are building nano engine right now, right? In quantum thermodynamics also there are many
there is some progress in Starling cycle, quantum Starling cycle, but in case of Otto or Carnot, I did not find any. But Carnot cycle, yes, there is.
You can talk about Starling cycle also, like how they built it.
एक मॉडल है ना ST5 ST5 मॉडल है ना स्टर्लिंग का माइक्रोजेन टेक्नोलॉजी है ऑस्ट्रेलिया का
अच्छा
वो डिजाइन किया 3.5 kVA का इंजन है जो वो बायोमास गैस से चलता है
क्या काम करते वो?
अभी तो वो प्रैक्टिकल में नहीं है, बस डिजाइन ही किया है अभी।
अच्छा अच्छा।
वो 3.5 किलो वोल्ट पावर सप्लाई करता है अभी। मतलब कि इसका जो पेटेंट है वो मार्केट में तो अभी नहीं है।
तो कंपनी का नाम क्या है? HT5?
ST5 वो इंजन है।
अच्छा
वो
Okay,
क्या
for
कहते हैं,
that
कंपनी हम
Starling cycle, I'll
ठीक है
हाँ
भाई।
स्टर्लिंग साइकिल पे ही है। लेकिन उसका पिस्टन अभी भी फ्रिक्शनलेस नहीं है, मतलब फ्रिक्शन है उसमें, बट
अच्छा
वो
ठीक।
काम स्टर्लिंग साइकिल पे ही करता है।
or that experimental realization of Starling cycle there is there. I will share that paper actually. I have not studied that, but there is a paper in Science 2016. So in that paper, they have first realized the Starling cycle in experimental realization with a single atom heat engine. So I have not studied that, but we can
Yeah, that.
look at for the experimental realization. That because in Starling cycle there is no adiabatic stroke. Adiabatic stroke is much more difficult to handle. Okay, I did not say that because in case of adiabatic case, though adiabatic case the time is very important because though it is I am considering the reversible case and these things also, but still in case of adiabatic the heat there is no change in heat d cross q is 0. So to control in case of experimental case, the adiabatic stroke is difficult to control. That's why the Starling cycle is much more easier to make experimental realization. So that's why they have made some experimental realization using the single atom. So I'll share that paper, but I have also looked at into that. I have not studied that paper.
Okay. Okay, overall, this is a very nice talk, Shuvodip.
Thank you. Okay, so if there is no question, then I can stop sharing.
Yeah, overall this is very nice, and means after Ravi's, we can combine things with Ravi's topic that at the quantum means system bath perspective means how we want to use them means depending on that means we need to understand the engine perspective or the dissipation perspective that dissipation perspective more important for the spectroscopy and transport phenomena, and this kind of engine perspective is more important in terms of designing the nano engines, and yeah, so this is a very new and important topic for most of us, I think. Okay, if there is no question, then
Okay, then I'm stop. Yes, yeah.